So, good evening, everyone, and welcome to today's session. So, today's session will be on solver modification. So, we look at how to copy a solver, modify it based on some equations, and then we'll try to solve one test case that is already present in our repository, and with the same solver, with the same modified solver. Okay. So, to begin with, the solver that we will be modifying is a scalar transport form solver, and we will be introducing a passive scalar with a flow that is already initialized. Okay, so the very first question would be, what exactly is a passive scalar? So a passive scalar is a quantity that is transported by a fluid. Okay, and when it is transported by your fluid, it does not affect your fluid flow or the physical properties of your fluid, such as density or viscosity. Okay, that is why the term passive, because the fluid is carrying it, it is not reacting by itself by the fluid or with the fluid. And these are very good when you're modeling something as pollutants, or if you have any tracers or something like that, you want to do any type of simulation regarding that area, you can do it using these passive scalars. Okay. And the reason why it does not mix is because the scalar concentration is generally very low, and because of that it does not create any of the buoyancy forces or does not change the viscosity that would otherwise change it if the concentration were high. Okay, so this is one example of flow over a cylinder. And now in this case, when we do a CFD simulation, we know that behind the cylinder downstream, you will have some vortex shedding or any vortices forming, right? So in this case, to visualize it, if you're doing an experiment, we have something known as a tracer. In this case, it is ink. So from the cylinder, you can see that there might be small inlets, and from that inlet, you have the ink coming out and mixing, not mixing, but rather flowing with the fluid. Okay. So in this case, the ink itself, it is not reacting with the fluid, but rather the fluid is transporting that. So that is why your ink becomes your passive scalar. Okay. So we will try to do something similar to this. We will first have a tube in which we will initialize the flow, and then we will introduce the tracer, and that tracer will move along with the flow. Okay. So this is a problem statement. We have a simple pipe. So this is a 3D geometry. This is the diameter of the pipe on the right, and on the left hand side you have the overall length of the pipe. You have the inlet on the left. You have walls on top and bottom, and you have the outlet. Okay. So let's take this cut section view only. And in this, we will first initialize the flow. Again, you will be solving your flow equations using the normal Navier-Stokes equation. So you'll solve for continuity and you'll solve for momentum. And once your flow is initialized, then we will introduce the passive scalar. Okay, now this part will be the one that you modified into your new solver. So in this, we will be introducing the scalar in your whole simulation. Okay, and the passive scalar will be initialized when the flow is fully developed. Okay, so that is the reason why we are first initializing the flow. We have a completely developed flow, and then we will introduce the passive scalar, so that scalar is only transported by the fluid. Okay, so this is your case structure in OpenFOAM. So in this case, in this particular case, you will have two blocks. One will be your flow block. This is where you will initialize your flow. So it's a simple flow in a pipe. So again, you'll have your zero constant system. You also have an all run, so you can run this whole case using just that all run script. So again, in zero, you will have your velocity and pressure. In constant properties, you will have momentum transport and transport properties. So a momentum transport is just whether you're running a laminar case or turbulent. Again, in this case, it's just a laminar case. And then in system, you have your block mesh and all the control parameters. The next thing you have is your scalar part. Okay. Now in the scalar part, you have again zero constant system. But in this zero part, in your initial boundary conditions for velocity, the U file, once you run your flow simulation, so it will run up to 50 seconds, we will be copying this particular file, your velocity file, from the flow itself. Okay, so once you have run up to 50 seconds, that last time step velocity, we will copy it into the scalar, because at time step 50 you will have the flow completely developed, and that parameter is what we require to initialize the scalar part. Okay, so I'll show you how to do that. And again, scalar will be the thing, this is the thing that we will be modeling into our solver. So again, this is a parameter that we have created. Okay, And again, then you have constant and system. In constant, again, in transport properties, there will be a few modifications. Again, based on the solver, we will be introducing a source term and the diffusion term for the scalar. This, as you see the equation later on, you will see that we are changing that diffusion term from dt to ds. Okay, so those are some minor changes in transport properties. Rest of the thing in system remains the same. So you'll have the same geometry. You'll have a few changes in the control parameters, and again, FE scheme FE solution will be based on the scalar part. Okay, yeah. So over here you see the velocity is derived from the flow field. Now your governing equations. So the very first thing you have is the flow field that you will be initializing. So to solve that, we'll be again solving the simple Navier-Stokes equation. So you have continuity, you'll have momentum equations, and it's a laminar case, so there's no turbulence modeling whatsoever. Okay. And for the scalar or passive scalar, in this case, this is the equation that we will be solving. And this is the same equation that will be added in your solver itself. Okay. So the very first term you have in this equation is S, that is your passive scalar, and dx by dt, that is your time derivative for this scalar. Okay. Then we have the divergence term for the scalar itself, that is given over here along with the velocity term. And then you have your diffusion. Again, you'll see that all of these parameters are mentioned in your solver itself. So you have the diffusion coefficient, and again with diffusion you again have your divergence of or your scalar, passive scalar. And lastly you have the source term for the passive scalar. In this case you can also refer to this as the reaction term. Okay, you'll see why exactly is this the reaction term. So again, this is your equation that you have. Okay, but in this case, we have a few things that we have to rearrange so that it becomes much more simpler when we are coding it into your solver. Okay, so first we will just rearrange this equation. So you saw that we have the divergence term on the right hand side, so we've just moved it to the left hand side. So there's a negative sign over here. Along with that, we also have the source term. So again, if we substitute the source term, we'll get this minus ks. Okay. Now, once you have this equation, okay, so for that reaction term that I said, let us assume we have a reaction or reactant A. Okay, so your reactant A is going to convert to B. So again, your reactant A is getting converted to product B in this case. So in this case, we just have one reactant. As it reacts, it gets converted to product B. So in this case, your A is getting consumed, whereas your B is getting produced. Okay, so keep this in mind when we are solving this. So if we take the previous reaction term that we had and we put it into this equation, we get minus KSA. So in this K is your kinetic rate coefficient, so this part, and the negative sign that is there over here, that will mean that the rate of reaction or your generation is negative. So in this case it is getting consumed. So if you have this particular equation, so in our case minus ksa, so in our case the rate of coefficient k will be determining whether your scalar is going to be in this case it's already negative, so it will say that your scalar is getting consumed in this case. Okay, now it may happen that if you have, now this is just for one scalar, okay, that's why I've labeled it as scalar A. See, if you have multiple scalars or you have multiple parameters that you want, now your scalar can be anything. Okay, it can be temperature, or it can be some pollutant or some molecule that you are creating or modeling or you want to model. So in this case, your scalar, if you have multiple, say I have three different scalars or two different scalars, so your scalar A will react with scalar B. So in this case, you will have A and B as your reactants, and you will have C as your product. So in this case, you will have A plus B, that both of them are reacting and they're getting consumed, whereas C is getting produced. So in this case, accordingly, your this equation will change. And based on this equation, when your sign changes, you will have to make some changes in your overall equation. Okay. So that is why in our case, we will label all of these equations for scalar one. Okay, you'll see that in a bit when we are modeling it into the solver itself, because when you have multiple scalars, again the sign will change, so you will also have to create multiple different scalars. So you'll have scalar 1, scalar 2, scalar 3, depending on how many you want to model. Okay, so again, once you have this equation, once you've understood how the reaction is happening, I will again show you how these reactions are happening. There's a proper documentation on this particular case, so you need not worry about the physics part that is going on. Just focus on how we model everything into the solver itself. Okay. So keep in mind that this is your scalar equation. Okay. You have dou by dou t, dou s by dou t, and then you have your divergence term, and then you have your um, you also have your the Laplacian term over here with the again divergence of s, and then you have your source term on the right. Okay. So this is the overall thing. So when you are modeling or coding this into OpenFOAM, since OpenFOAM is in C, C++, you cannot directly just type dou by dou t and expect it to understand. Okay, so you have to break it down into simple C language. So over here, your first term that you have, that will be as d dt of s, in this case scalar. Okay, and over here I've just written s, but in the actual code we will write it as scalar one. Okay, and then your divergence term over here you have, that will be as div, and then you have u and s. Again over here these are just names I've just given it so that you understand it, but in the actual code you will assign it the proper value that OpenFOAM will understand. And then you have negative Laplacian ds, that's your diffusive term. And again over here previously if you see it in the original code, it will be dt. In our case we are just modeling it to ds, and again you have scalar one. So in this case we have diffusion for scalar one, so ds. Okay. And lastly you have your source term. So in this one you have ks. So in this case this ks is just the kinetic uh, the kinetic part, kinetic rate coefficient of scalar one. Okay, so that is why I've written ks. And over here you have the actual scalar one or scalar a in this case. Okay, and for our particular case that we will be running, we have kept diffusion 0, and we've also kept the source term as 0. Okay, so you'll see why exactly is it 0, and later on you can change it and maybe see what happens. Okay, so first we will modify the scalar transport form in OpenFOAM 9. Okay, so again the path to your solvers I had shown you guys before also where you can find it, but again I will go back to this, where exactly are your solvers located in each of these versions, so in OpenFOAM 9 and OpenFOAM 24.12. Okay, so the very first thing you can do is actually, before going to the solver itself, I've already shared the files, so you need not do this, but if you want you can download it for other cases. So you can go to our website and you can scroll down on the left hand side, you'll find lab migration project. You can click on lab migration, scroll again down, go to completed lab. Okay, and under completed lab you will have the very first one, stimulation lab by Shivnadar University. So this was done by Professor Dheeraj. It was proposed by Professor Dheeraj and completed by Manzil. So you remember Manzil from yesterday. He performed a demonstration on dynamic meshing. So this case is done by him as well, the solution part. So you can download the very first example. This is experiment one. Okay, so you can view solution and you can download the solution. You can click the solution drop down menu and click on one, and you can download the solution. So over here it will show that you have the main source file. So your zip file is there. Within this, you'll have all your case files. You also have the modified solver within this, and you also have a PDF. Okay. So the PDF is just the report, and everything that I've explained about scalars and all, it's mentioned over here in detail with links to proper physical to the proper physics that you are going to be solving in OpenFOAM. Okay, so you can download this case because all of the case files are based on this itself. Okay, so if you okay, so if you were to just download the PDF or the report, so this it will look something like this. Okay, so this is experiment one, and if you scroll down you have the governing equation then models, so you can click that, go to governing equations. So over here again everything is mentioned. You have the governing equations for the flow part, then you also have it for the scalar part. So in this case passive scalar s1, so they're taking one scalar. The reason why they have put s1 is because in the later experiments they have introduced another scalar, so you just have to make a few modifications in the code to incorporate scalar 1 and scalar 2. Okay, and regarding how exactly are we solving for this equation, there's a theory. So you can, I'll just right click and open it in a new tab. So there's a hyperlink over here, and over here you can see there's a proper detailed explanation of how these equations are set or how do you solve these equations. So again if you scroll down, everything that I said about the reaction part, how exactly is the negative sign there, and if you were to introduce another reaction, how would the sign change. So based on that your equation will also change. So again if you have say equation, if you have solution You have a reactant A to B. So all of these things that I just now explained, it's all in this document. So you can read this, and it will help you better understand what exactly are we doing in this particular case. Okay. So yeah, coming back to the presentation. So you've seen the equation, and now let's modify a pre-existing solver in OpenFOAM to the equations and the solver that we require. Okay. So in this case, we have a solver. So if you're in OpenFOAM 9, now these cases are all for OpenFOAM 9, but again, I'll show you where exactly it's for OpenFOAM 9 and for 2412. So if you're on OpenFOAM 9, you will go down to OPT in your Ubuntu. Go to OPT, OpenFOAM 9, and under OpenFOAM 9, instead of going to tutorials, you can go up to applications. Okay, so in applications, you have solvers, and then in solvers, you can go to basic solvers. And over here, we have to copy this scalar transport form. Okay, so if you open the scalar transport form, you'll have a .c file, you'll have a header file, and you'll also have some files that are required to properly execute and to import any libraries that are dependent on these solvers. Okay, so we have to copy this scalar transport form into our run. You can copy it into your run directory, or you can create another folder as well. Okay, so again, this is for OpenFOAM 9. If you come back to Ubuntu, and if you're on OpenFOAM 24, 12, or any of the ESI versions, you can go to user, you can go to lib. Under lib, you'll scroll down, you'll click on OpenFOAM, and under OpenFOAM, you go to 2412, and then you again go back to applications, application solver, and over here you'll have some additional solvers which are not present in OpenFOAM 9 or in any of the org versions. But again, if you want, you can modify any of these solvers. I'll just show you how to modify the scalar transport form. So again, over here also you have scalar transport form under the basic solvers. Okay. So let's go back to OPT, OpenFOAM 9, application, solvers, basic. So let's copy this entire scalar transport form into my run directory. Okay. So again, over here, we have, if you want to go back to your run directory path, you have Ubuntu home. Under home, you'll have your username, and then you'll have OpenFOAM, and then you'll have your version, OpenFOAM 9. Now you can copy the the solver into your run directory. You can create a new folder, and you can just paste it over there. But this is a preferential choice. You can create an application folder. Like in my case, I've created one applications folder outside my run directory. But again, this is optional. If you want, you can create this folder. You can just create a new folder, or you can do it through your terminal as you did for your run directory. You can do so. I can just right click, open in terminal, just go to WSL, open form 9, and then over here you can use the command mkdir, and you can make applications. Okay, so you can do this. You can create a folder using this way, or you can just right click and create a new folder. I like to keep all of the solvers outside my run directory, because at a glance, if later on you want to check which are the modified solvers, you can just open this folder rather than searching in your run directory. Okay, so let's copy it over here outside the run directory into an applications folder. So I'll just paste it here. Okay, so once you paste it on Windows, you'll have these additional zone identifiers. Let's delete that. Yeah. Okay, so ideally, once you copy it, you will have these files. Okay, so before we begin, you have to change your solver name to something that does not exist in OpenFOAM. Okay, so in this case, scalar transport form already exists. So if I were to modify this and just save it, it will try to override the pre-existing scalar transport form that is already present in OpenFOAM. Okay, so we don't want that. So we'll just add a name, new scalar transport form. Again, this is again a preferential choice. You can label it as just STF if you want scalar transport form, or you can put in your name, or if you want, you can just label it as anything you want that you will remember. Okay, so this name is very important because your solver is depending on this name. Okay, so in our case, we have labeled it to new scalar transport form. Okay, the folder has been renamed. We will also rename the .c file. So we'll label this as new scalar transport form. Okay, now before opening these two files, we'll go to the make folder. So on top over here, you have the make folder, and within this you will have files and options. So let's open both of these, because you have to make some changes in this, and these are quite important as well. Okay, so yeah, so first we'll open the files. So again, over here, files, what it is going to do is the very first line, it's going to read the .c file that you have. Okay, so this is your backbone of your whole solver. So everything is based on your .c file. So again, we've renamed that to new scalar form. So let's rename this as well to the new solver name. Okay, so you rename the .c file to the new solver name. Along with that, over here also you will have the scalar transport form. We'll change this to new scalar transport form. Okay, so you have new scalar transport form. Now another thing to make changes over here, you'll have exe to execute and under form app bin. So we don't want it to execute this under the original app bin or the application bin for OpenFOAM. So over here, we will change this to user app bin. Okay. So you just type user and then you type underscore. So the reason for doing this is we are letting OpenFOAM know that this particular solver that we are developing or modifying, it is going to be under the user application bin so that it does not cause any problem in the actual original files that are present in OpenFOAM. Okay. So always make sure that you are in your use form user app bin and not in the original OpenFOAM app bin. Otherwise you will mess up your whole installation. Okay. So always make sure that the user is always put in properly. So these are the only changes that you have to do under the file section. The next thing you'll have to go is to to the options part. Now in options part, you will have again exe include and execute libraries. So these are some of the libraries that will be required by a solver. So in this case, finite volume, because we're solving FPM schemes and all of those things. So it's required. You also have some meshing and sampling cases. In this case, again, these libraries are depending on your C file. So you'll see over there that we are importing some header files. You'll see that in a bit. So again, these libraries are important for the proper execution of your solver. Now, in this case, we are just copying the scalar transport form, so we don't need to make any changes in this particular file. But say if you're merging two different solvers, so say if I wanted to merge simple form and the scalar transport form together, then I would require to import some of the libraries that will require to execute both of those solvers together. Okay, so again, if you're merging two different solvers altogether, then you will require some more libraries that are depending on those particular solvers itself. Okay. So these are the only changes under files and options for now. And yeah, so let's close this and go back. Now over here, you will have create fields, that is your header file, and you will have the actual .c file for your solver. Okay, so let's open the new scalar transport form .c file. Okay, so over here in the beginning, it will just give you some basic information of what exactly is going on over here in your file. And under application in the commented section, you can change this to new scalar form, scalar transport form. Okay, so again, this is just preferential work. If in case you open this solver and you just want to glance at what exactly is the solver, you will know that this is your modified solver. Again, you can label it as new scalar transport form or anything you want over here. Okay, so this is just at a glance. If you open your file, you can see that this is the modified file and this is not the original scalar transport form file. Okay, so under applications, you make this change. You can just save it as it is. And then over here, the very first thing you will see in this block is you're including some header files. So in this one, you're including fpcfd dot header file. You are also including FE models, FE constraints, simple control. So all these are required for the proper execution of your code. So for CFD and models, these are some of the code that will be required. Now again, in these particular files, you're just doing top level coding. You're not touching anything that is like the equations or anything in depth. You're not touching. You just mention something like div schemes or divergence schemes or whatever you want, and OpenFOAM will know. So you are not programming anything in depth. Okay, so all of these header files are where OpenFOAM knows that these equations have to be solved. These are some of the discretization schemes that are available, and you just have to mention them. So for those things, you have to mention these header files. Again, simple control is just when your whole simulation is running, some of the control loops that are required. So it's all of these header files. Okay, then from the next line, then your actual code starts. So again, over here you have your main. So if you know basic C++ coding, you know your int main is where you exactly put your actual code parameters or your actual code that you want to run. So within this, again, we'll include some header files. So your time header files, your mesh header file, any of the root case or listing header files, those are all included over here. Okay. And then we have the simple control, in this case, simple mesh. So again, your simple control, I've just typed it over here, but it knows that there is this header file. So it knows that it has to access everything from this header file. If I were to remove this and just type simple control, it would throw an error saying that it does not know what simple control is. So again, in C++, you must have learned this, that for executing anything, you require either to mention it beforehand, what exactly is that doing, or you can add a header file itself. Okay. And over here, you'll again do include create fields dot header file. So in this case, we already have the create fields, so it will access anything that is there within that folder. We'll look at that also in a bit. Okay. Then over here, this info part is just some things that it will print on your terminal. So when you're running a simulation, it will just print calculating scalar transport form. Again, over here, you can change it to calculating new scalar transport form. So it will just display that this is the new scalar transport form it is running. And then you have your current number header files. So again, based on your simulation, whether it is diverging or converging, it will be based on this current number. So for that, you already have the equations in open form. It is just accessing those equations. Now over here, you'll have the loop from where it starts. So you'll have the while loop and you'll have the simple loop within it. So within this, it will solve. So anything put within this particular block, it will execute it again and again iteratively. Okay. So in your while loop, you have again info time. So as your time progresses, all of these parameters will be updated. So again, you have FP models, which is accessed from the header file, and you'll have again another while loop. And over here, you'll have the actual code. Okay. So now if you see, I mentioned that over here, when we were seeing the actual code, this is your physical code that you write it in normal human language. And this is the one that is understood by the computer. So that is the reason why I wrote all of these things in blue. Okay, so if you see the code over here, you'll have d by dt. So in this case, ddt of t. Now in this case, t can be either your transport equation or the scalar itself, or in this case, it is temperature, because they are solving for temperature in the actual scalar transport form equation, in the actual real scalar transport form solver. So in this case, they're solving for temperature. In our case, we want to update it for a scalar. So we just label it as scalar 1. So in this case, you have d by dt of t. Over here, then you will have FVM of the divergence scheme. So again, over here you have phi, that is your u, and or your flux. And over here you will have t, again your scalar. And then you also have minus over here. So if you look back at the equation, you have d by dt of scale of the scalar. Then you have the divergence term, so plus divergence term, and then you have minus the Laplacian term of your diffusivity and the scalar. So it's the same thing over here, diffusivity and scalar. So we'll change some of these parameters based on our preference, and equal to. So over here, if you again go back to the code, equal to, then you have your source term. So in this case, you have FE model source term, but we'll modify this based on our equation. Okay. And then we have some of the relaxation and solution parameters. These will be recognized by the FE solution part. So again, we have to update all of this based on the new equation that we have. Okay. Now, how will you know exactly what is DDT, and how will I know if I want to put, like, if I'm writing it in a physical sense, how will I know that what is the equivalent in open form for it? For that, you have the open form programmer's guide. So again, this I've also linked this in the PPT itself. So you can download this open form guide and you can go through it. It explains also how OpenFOAM is written, the codes within it. It also explains your basic CFD terms like tensors, scalars, vectors, all of those things that OpenFOAM uses in the backend. So you can go through that. So again, over here you can see the mathematics behind CFD. You also have discretization scheme, dimensional units. So you can go back, you can directly click it and go to dimensions. So if you notice that in OpenFOAM, in your U or P files, in your velocity or pressure files, you will see that we mention on top the dimensions. So what exactly does this numbers mean? We type this. So over here, it gives you exactly what it means. So the very first term is for mass. The second term is for length. Third one is for time, then temperature, quantity, current, luminous intensity, and again in what unit it is in. So if you want, you can convert all of your simulation data into these units and then you can input those. Okay. So again, if in our case we will be changing it to these parameters. So if you want to see the dimensional units, what is it? You can go through this document. And also, if you scroll down, you'll have under discretization procedures. You can read all of this. You have your gradient schemes, or your gradient terms. You'll have divergence term, curl terms, Laplacian terms. So all of these are there. And there is also a table at the bottom of all of this. So when you scroll down, you'll have over your volume scalar field. So if you notice that in your code itself, I'm not sure if it is in this code, but yesterday Manzil was showing something about volume scalar fields and all. In dynamic meshing, he opened the source code for it, and he showed you what exactly is going on within that. So you'll see that there are some things known as volume scalar field or surface vector fields or all of this. So again, those are mentioned in this documentation. How can you implement that? How can you modify those? So based on that, you can again read this and modify it accordingly. And equations, partial differential equations, you have PDEs, so on and so forth. So how exactly it is modeled, it's all written in this. And once you come down to this table at around 35, page number 35, you will see that for Laplacian, so if I were to put Laplacian, you will have implicit and explicit. So you will have FVM and FVC. So FVM is your finite volume method. Yeah, hope it's visible now. So FVM is your finite volume method, whereas FVC is your finite volume calculus. So based on this, you can determine whether you're solving for an implicit or an explicit term. So again, you can model that or you can change that within this. So over here we mentioned FVM, FVM, FVM. You can also change it to FVC. Now in our case, everything is in finite volume method, so we'll just leave it as FVM. But in some cases, like if you open simple form or you open the source code for simple form or any of the flow solvers, you will see that some of them might use FVC in them. So you can always cross check it with the solver itself. And if you don't understand what does that term mean, you can open this document and look at it. So again, over here, if you want to define a Laplacian term, you can just type Laplacian and then your term within it. Same goes for time derivatives. So if I have just dou by dou t of phi, so in this case, I'll just type ddt and add the unit or the term itself within it. Same goes for second derivative. If I want to add a double derivative, so over here d2 dt2. So this is just like d square dt square. Okay, and then you again type in your terms or your parameters that you want to solve for it. Same goes for convective terms. Then you have divergence. Over here we type div. If you have a gradient term, we type grad. So when you were seeing the numerical schemes, you saw that we were mentioning div schemes, then grad schemes, and also we were mentioning something known as SN grad when it came to the meshing part or parameters that are dependent on the meshing itself. So again, all of these are mentioned over here. If you also have a source term or a curl term, you can put all of those as well. Okay, so go through this document. If you want to modify anything in the future, it's always beneficial to know how to determine all of those terms in open form so that it understands it. Otherwise, you might get a ton of errors when you're modifying any of these codes. Because even if you miss a simple semicolon, it will throw an error saying that this particular code is not going to run and kindly check this particular line. We'll see that also how it throws an error. Okay, so now that we know how can we or what exactly does this DDT mean and how can we determine it or type it within this code, we'll try to modify it based on this equation. Okay, so now we'll modify the pre-existing scalar transport form to the new scalar transport form. Okay, so the very first thing we will do under this block only. So we'll first modify only this piece of code. So we have FV scalar matrix. Okay, and over here we are telling it that this is the T equation, and this particular T equation will be in your this one in your create fields header file. Okay, so over here whatever changes you make, you also have to make changes in your create fields header files. So over here let's change this to scalar transport form. Let's keep it small. Scalar 1. Okay, so again over here I'm keeping it for 1 because as an assignment I want you to add another scalar. So over here I'll just add it as scalar 1. Okay, so scalar 1 equation, this is our equation that we will be solving for. And the very first thing we saw is d by dt of s, so that is scalar. So over here we'll again label this as scalar 1. Okay, the next thing we have in the equation is your divergence plus divergence of u. comma s. So in our case we have flux, that is u, and then we have t, in this case scalar, so we'll type again scalar 1. Okay, and the next thing we have minus the term for your diffusion term. Okay, so we have Laplacian, in this case Laplacian of the divergence term along with the scalar. So in this case it is the diffusion term is set to dt. Let's change this to ds1. Okay, so if you want to set your diffusion for another scalar, you can set it to ds2. Same goes for a third scalar, you can set it to ds3. Okay, so in this case we'll set it to ds1, and for t again we'll change this to scalar. Enter. Okay, and now we will add our source term. Okay, so in this one we want to add this particular part into the code. Okay, so let's delete this. We don't require FE models source this. We will type in a custom thing. So over here it is minus. We have typed ks in this way, scalar 1, ks1 multiply. Let's not leave any space. Let's see what happens. And then we'll type scalar 1. Okay, so over here in this case we have your kinetic coefficient with the scalar itself multiplied with your scalar, so that is your ks. Okay, so we have this particular term written over here. Okay, so again if you have multiple scalars you can change this number from ks1 to ks2 3 4 5 whatever you want. Okay, and now next thing we will modify is this particular part. Now since we have modified this name to scalar 1 equation, same goes for over here. We'll change all of this to scalar, so small scalar 1 equation, and over here same goes for FE constraint. Change this also to scalar 1. Okay, same over here. Let's copy this scalar 1, and over here in t we'll change it to scalar 1. Okay, so the changes that you have to make for this particular code is first the name of the equation or the block itself, so scalar 1 equation. Then we will make the modifications under the terms itself. So we are introducing this scalar 1 term. So everywhere where it was t, you change it to scalar 1. Same goes for the diffusion term. You set it to ds1, and then you also modify scalar 1. You add the source term for the kinetic part, and then you have your scalar 1. Okay, and yeah, again same goes for here. Since we have modified the name over here, the same change goes over here as well. Okay, and over here we'll just type it's written over here runtime, right? So all of these things will be written when it is running. Okay, and over here it is end of the loop. So once your simulation is run, it will just give you a, a write up on the terminal saying end, or the simulation has ended, and then over here your loop is getting over. Okay, so this is the while loop or your whole interloop. This is the end of your while loop. Okay, so once this thing is done, you can save this with the changes in place, and then you can move to the create fields header file. Okay, so now your create fields header file, it will again display some basic info in your terminal. So over here it will say reading fields. So t, in case of t, we will change it to scalar 1. Same goes for volume scalar fields. We change this to scalar 1. Okay, now over here it will read some of these things, or it is required when you are solving these. So in your 0 folder you might see that some cases require velocity, pressure, some might require temperature. So all of these are determined by this, whether it is important or not. It is determined over here. So over here you see that the term t, so in this case scalar 1. So now in our case, with the modified case in place, you will have to have a folder named as scalar 1 in your a file named as scalar 1 in your 0 folder. And this will be again the runtime time name, at whatever time it is running. Along with that, it will also look up whether it is required or not. So over here we have said that it is a must read. That means it has to be there present. If it is not there, it will say that this particular file is not present and please add it, or it will just keep showing you an error. and auto write. So whenever your simulation is running, it will, in each of those folders in your run directory, it will show up over there with the modified values. Okay, so auto write, and over here then it closes the loop along with mesh. Same goes for info. It will read the velocity files. So in this case, we have velocity. It's going to read again whether it is important or not. You can determine it from here. So again, for velocity, we don't need to make any changes over here. And once these are the properties that you will require. So these are all your zero folder properties. So you have, so we'll require for a new case scalar one and the velocity file. Okay, so these two are two important files that we will require. The next thing we'll make changes is in the transport properties. So over here it will again display reading transport properties, and within transport properties again must read if modified. So all of the parameters that it requires, it will read, and in this case it is written over here no write. So when your simulation is running, it won't write anything as such within this, because your transport properties is within your constant folder, and your constant folder has all the constant properties that remain constant throughout your whole simulation. So in this case it's not going to write anything as such. So it is only going to access all the data that is there in it. So in this case we will introduce the diffusivity term. So in this case it's dt, but we have modified this dt to ds1. Okay, so ds1 has been modified. Same goes for over here, dt to ds1, and to look up ds1. Okay, so now in the original case, if you open the transport properties, I'll show you. So yeah, this is one tutorial. So we have the case files over here. So this is the scalar transport form files. So you have under 0, you will have velocity and temperature. Okay, so this is one of the tutorials from the scalar transport form folder. So we have velocity and we have temperature, but now this temperature, we will modify it. We have modified it for scalar 1. So this name will change to scalar 1. Same goes for under constant, under transport properties. You'll see that over here we have dt, the diffusivity term. So in this case dt, and this is the units for it, and in this case it's set to some value. So in this case, we will change this dt to ds1. So that is what we are doing over here. So when it is reading, it will read for dimension ds1, and we are saying that within transport properties, it has to search for the term ds1. So if I were to just copy this particular folder and run it with my new solver, it would throw an error saying that ds1 is not specified or has not been mentioned over here. So we'll have to change this from dt to ds1. Okay, so that is what we're doing over here. And additionally, we will also be mentioning the kinetic term that we have. So let's copy one of this part only. And let's paste this here. So that is this part, okay? This one, your kinetic rate coefficient, Ks. Yeah, this one, okay? So this K part. So this is what we're going to copy into. We're going to add into the transport properties. So let's change this reading instead of diffusivity. We'll change this to kinetic rate coefficient. And we will change this to from dt for ds1 to ks1. Okay, same goes for here. We'll change this to ks1, and here also it will look up for ks1. So let's save this file. Now we have made the changes. Okay, so we've added two terms over here, or we modified one term and added another one in your transport properties. So now it will require diffusivity as ds1 for scalar 1, and it will require the kinetic rate coefficient for scalar 1 as ks1. Along with that, it will also require in your 0 folder, instead of t, it will require scalar 1. Okay, so now in this case, this one for transport properties, you will have this as ds1. Same goes over here. Let's change this to ds1. You can keep the value as whatever it is. So in this case, we have set it to 0, and you can copy the same one for the kinetic rate coefficient. Yeah, okay, this one, the kinetic rate coefficient. So we'll change this to ks1. Now the dimensions for this is different. So it is, this one is 0. So it's for seconds. Okay. So this is your second part. So it's second raised to minus 1. So this is the values that you have to set. Okay, so these are two things that you have to modify in your code. So you can save this. Now I'm just running it within the scalar transport form only. Okay, so this is the tutorial for it. So I've made this change. Along with that, within this case file that we're running, 0 from T, I will rename this to scalar1. Okay, so we'll rename this to scalar1 and everything within that also. So under object, you can rename this to scalar1 and yeah, and then maybe keep the value as 1 only, or you can change it. You'll have to change some of these boundary conditions because this was for the scalar transport form. The geometry itself is a little bit different. In our case, we just have inlet, outlet, and walls, and front and back is not there. It's a 3D case. Okay, so you just have inlet, outlet, and walls. So again, you can change this according to that. So that is why I said that you can download the case directly, so you don't have to make these changes over here. Okay, but if you want to see where exactly to make changes, so these are some of the changes that you have to make. Okay, so now we have modified this solver. Okay, so we've added first. So firstly, what we've done is you copy the pre-existing solver from one of the solver cases in OpenFOAM. Okay, so you copy, you will have the make folder, you'll have create fields, you'll have scalar transport field or some of your folder or your solver file, solver.c file. Along with that, in some cases, you might also have the equations for each of the cases. Like for velocity, you will have an equation, for temperature or for energy, you might have some equations. So some of those additional files might be there. I'll show you how the case file structure is for simple form. So in this case, we just have a very simple code. We just have .c file, we have the header file, and within make you have files and options. So again, first you make changes in your files, you change the solver name, and make sure that you are in your user application bin, so your user app bin. Okay, and options you can change if you require any additional libraries for your solver. You can add those. Then you come back to your source code, your .c file, and within that you can change the equations based on your new solver, and then you can change your create fields or header files that are depending on this C file. Okay, so now once you have made these changes, you have to compile your solver. Okay, so now you can right click and open in terminal. So you have to make sure that you're within this particular folder. Okay, not outside this folder, not over here, but within this folder, so within your solver itself. So open the terminal. Within that, type WSL, open form 9. Okay, so now if you see, I have these folders. I have the make, the .h file or the header file, and the .c file. So first you will do is w clean. Okay, so you're just cleaning your entire case. If you've already compiled something previously and it was not proper, or you want to overwrite something, it's always better to clean the case. Okay, so your clean, w clean, is similar to your all clean or your foam clean tutorials command. Okay, but this is for the solver part. So you have w clean and then you have w make. Okay, so once you do wmake, it will compile your solver. So see, in this case, it is saying that it is giving me an error, saying that in your .c file, you have an error between at around 43, 67 to 43. Error is that it has this um, bracket. Okay, so let's see. So let's go to the .c file, and over here, it says that we have this bracket over here. Within that, it also says, so let's see. It says that there's a token scalar, it has a bracket. So in this case, I think it is throwing an error saying that it doesn't understand scalar 1. So we've only labeled it as scalar. So let's change it to scalar 1. Let's save this and let's do w clean again and w make. Okay, so usually when your compilation takes a long time, it means that it's running properly. When it happens too fast, that time you know that you will get some errors. Okay, so always if you get any errors, it will show it in bright red, or depending on your uh, terminal settings, it will show it as error, and then it will show exactly where is the error. So in my case, within my .c file at line 67, under this line over here, I had an error, so it couldn't understand scalar, so I had to name it as scalar 1. Okay, so again, now this is a pretty simple code, so it's easier to not make mistakes. But again, when you're merging two different solvers altogether, you might get some problems in the beginning. Okay. So once your solver is done, now OpenFOAM knows that there is a solver named as new scalar transport form. Okay. So previously, if I were to type new scalar transport form, it would just throw an error saying that this solver does not exist. But now if I type this name, it will run the simulation using this solver. Okay. So you can close this terminal. So now your solver has been created. Okay. So you've modified your solver, you've cleaned it, and then you've compiled your solver. Now the solver has been created. So again, I've created under application. You can create it in your run directory also. So in this case, we have this case files. Okay. So now if you copy directly the folders from the tutorial that I showed you, the lab migration, you will have two folders. You'll have the flow folder and you'll have the scalar folder. So under the flow folder, if you go to system and you go to control dict, it is using the solver simple form. Okay. So because we just want to initialize the flow, so we're just using simple form to initialize that whole flow. So we have a fully developed flow. Okay. And we're running it from 0 to 50 seconds. Pretty simple. Okay. That is for the flow part. Again, all of the simulation parameters are laminar, so you don't have any problem in that. Then we go to scalar. Now this is the new scalar that we have created. Okay. So under scalar, you will see that we have this zero. Under zero folder, you will have scalar one and velocity. So if you open scalar one, you see that over here we have given inlet uniform velocity and outlet a zero gradient and wall also a zero gradient. Okay. Because we are giving some scalar value at the inlet and then we wanted to travel with the flow. So however the flow is developing, it will just travel with it. You'll see that how it happens. Okay. Velocity, again, velocity, this is the file that will be copied from your flow field. Okay. So if you were to just see it this way, it would be something like this. You would only have scalar one, you won't have velocity in the beginning. So let's first run that thing and then I'll explain each and everything in depth. Okay. So first we'll do, there's an all run file. We'll try to run it through the all run file itself. Okay. So I'll just change this to 4 processors in parallel because I have 6 cores. I can use 6, but again, it's better to leave 1 or 2 cores free. Otherwise, your Windows system crashes. So what is this all run file doing first? It's first going to do block mesh. Then it will decompose my mesh. So again, decompose par. We'll change that decompose par under system. Decompose par dict. We'll change it to 4. Okay, because I've changed that thing in. If you have many cores, then you can keep it at 6 itself. So first it will do block mesh, create my mesh, then it will decompose par, it will do the decomposition of my mesh, and then it will run this whole simulation in parallel using 4 cores of my system. And then in the end, it will reconstruct. Okay, so this is what is happening. Another thing to note is under the control dict, you will see that we are using the feature for purge write. Okay, so you see purge write over here, it is set to 1 because we are only interested in the final result for the flow. We are not really interested in having each and every time step. So what we are doing is we are only keeping the last file in this case. Okay, so see, I'll show you what happens when you use the when you use purge write in this case. So let's open it in the terminal. It's clear. Yeah. So now when I do all run bash all run, okay, just increase the size a little bit more. Yeah. So again, you can do bash all run. It will first do the mesh, then it will create, once it is done with creating the mesh, it will decompose the whole mesh, then it will run it in parallel. And when it is running, it will only log the very last file that we have. Okay. So let's wait for this to happen. I'll show you how exactly does your purge write work run. Yeah. So here it is decomposed. It is decomposed it. Yeah. So it has created 0, 1, 2, 3. And here it is running a simulation. Okay. So now over here the delta t is kept quite large, but again, this is just a demonstration case, so you can keep it quite large. Yeah. So here you see 0 constant, and it will log every file after 10 seconds. Okay. So let's wait for it to complete up to 10. Okay. While that is happening, yeah. we have some additional functions that are there, like surface fields and all. So again, as last time we saw for post processing, if you want to post process any of the data, you can add it under the functions tab. And within this, you have type the library in which you are trying to copy this from or access it from. And over here, you'll have some other parameters that you have to set. In this case, you have scalar field. We don't require scalar in file. But again, I think these are just by default. And you don't really need to stress too much on this part for this particular demonstration. Okay. So it will log after every 10 seconds. So let's see. It has become 13. So if I go back to this file, so we have now a folder 0 and then we have 10. Now once it crosses 20, if we were not using purge, we would have 3 folders, 0, 10, 20. But now since we are using purge, now it's crossed 20. So you'll see it has just updated that whole system or the whole case files from 0 to 20. Okay, so that file that was there, the folder 10, it has first logged the folder 20 and then it has deleted that previous file. So it will only log one particular time step at a time if you're using purge 1. If you were to change purge to 2, then we would have 0, 10, 20. But once the folder 30 is created, it will delete 10 folder. Okay, so it will delete the folder 10 and it will keep only 20 and 30. Once 40 is generated, then it will delete the folder 20 and it will keep 30 and 40. Okay, so you'll see over here as it is. So that is a feature of purge, right? So if you have limited storage and you're only bothered in the final part of your simulation, you can always use purge based on that. Okay. So this was about the flow. Let the flow happen in the background. We'll look at the scalar part till then. Okay. So now in our case, in the 0 folder, you'll see that we have modified the new solver. So we'll have scalar 1. And under constant, we had also made some changes for the transport properties. So let's open this. Yeah. So now in transport properties, we have the diffusion term and then we have the kinetic rate coefficient. So diffusion term over here, we've given both of these are set to 0. If you want your scalar to diffuse, you can change this value. But in our case, we just want to see how does the scalar get transported during the whole simulation. So that is why we're keeping it to 0. Same goes for rate of reaction. If you want it to change, you can change these values. Okay, so these are the changes that we did. Previously it was just dt. Now we've mentioned it as ds1 and ks1. So these two new parameters are required. Okay, so this is one change that you have made in your new solver. And let's delete this. Yeah, and under your control dict, now if you see, the solver name will be new scalar transport form. Okay, so you can use now your new solver that you have created. So in this solver, we are doing is starting it from 0, ending it at 15 seconds. Again, the delta t is quite small for this one. So this simulation will take some time. Okay, so on my system, when you're running it on 6 cores, it takes around 10 to 15 minutes, not more than that. But again, if you lower the number of cores you're using, it will obviously take some more time. Okay, so keep in mind that this particular simulation will take some time, but not too much time. Okay, so again, over here you can we'll change this in advance. So decompose, instead of 6, we'll change this to 4. Let's close this. Go back to scalar, and same goes for the all run part. We won't use all run though for this particular section. I'll show you how can we run this case. Okay, yeah, so I think the flow part should be done by now. Yeah, so okay, so see, once we have run the whole simulation, we've done the simulation has ran till 50 seconds, and after that automatically using the script has reconstructed the last time step, in this case 50. Okay, so under 50 you will see that we'll have pressure, velocity. So if you open this velocity file, you will have all of these vectors and all of the values already in place over here. Okay, so we want this particular file for the scalar part because your simulation is already run. In this particular file, it is showing that velocity is completely developed, or your flow field within your domain is developed. Okay, so yeah, let's copy this into the scalar folder under scalar 0 and this part. Okay, so now we have the updated velocity file and we have the scalar part. Now if I want to run this particular simulation, I'll just open this terminal itself. So we can go back one folder. So you can just type cd dot dot. You'll go back one part. And now we have flow and scalar. We'll type cd scalar. Okay, so now we've entered my scalar folder. So first we will do is block mesh. We just create the mesh. If you want, you can copy the poly mesh also from that flow file because it's the same geometry. But let's do block mesh in this case. Okay. So once we do block mesh, so I'll show you how can you run this in a single core because we'll be using the solver name. In parallel, you can run the same thing in parallel as well. So now once you've created your mesh, I will type in the solver name, but the new solver name. So in this case, new. When I press tab, instantly it knows that this particular solver exists now. If I do not compile my existing solver, it will not show anything. It will just show that new scalar transport form does not exist. So in this case, it is existing. So it is now going to solve using my new solver. Okay. You can run the same thing in parallel as well. So in this one, it said that it has some problem. Punctuation mark in line number 17, DS1. Okay. So let's check what exactly is the problem. So it says that under these particular file, new transport form, under transport properties, let's go to this file, transport properties. Yeah, so DS1, it says that there is some error over here. Let's see. Punctuation token and 17. This is there though. It's not a space. Okay, let's cross check this once with the files that are run. So under case files, yeah, we'll check this one. Scalar, scroll down. Yeah, I'm not sure exactly why is it throwing an error because it's the exact same thing and I've already ran this case. Okay, so it's fine. So ideally it shouldn't show that error. Maybe it's some other problem. So ideally, if you run this case, it runs fine. I don't know why in our case it is giving an error. Anyways, so once you run this, it should run your simulation as it is. And once your simulation is run, you can visualize it. So I'll show you the results. Over here, I already have the same case run with no changes whatsoever. Maybe there's some error with that particular case. So let's see. WSL, OpenFOAM 9, ParaView. Okay. So now when I type ParaView, I'll show you what exactly is the problem with ParaView itself. So this is the geometry that you have. It's a 3D pipe. And if you see, when I see, I can only see velocity in this case, but we want to see scalar. Okay. So over here, you can click scalar as well. And now it will show you your scalar properties as well. Okay. Sometimes it may happen that your ParaView is not listing out all the fields that are available. So you have to cross check whether all of these fields are checked over here. Okay. So over here we've shown that here that there is velocity and there is scalar one. Okay. So let's take a slice because this is a 3D geometry. So I'll take a slice in this direction. Click on apply and let's take this way. Right. We'll check where exactly the scalar coming from. So it's coming from this end. Okay. So this is your inlet part. So we'll rotate it this way. Yeah. So this is your geometry. So if you see for velocity, you have a fully developed flow because we already run the whole simulation previously for flow. That's why you won't see any disturbances in the flow field itself. Okay. So you see this is the flow. Once you run it up to 150 seconds, it will run. So there's no change in the flow itself because it's completely developed. It is set properly. Okay. So let's go back to 0. But if you see the scalar, in this case, we have some particles. Now this scalar can be temperature. It can be any particle that you want. So say it is some pollutant or something like that, or some molecules that you want to see how does it flow based on time in your simulation or in your fluid. So you see if we have the scalar, so you see in the beginning, it will then move along with the flow. Now, since this flow is a laminar flow, there is zero disturbances within this scalar. But say if you add an obstacle over here there'll be some vortex shedding or something like that. The scalar will also try and move along with that flow. If there is any vortex shedding, it will move along that part as well. Okay, so this is just a simple example of how does a scalar work and how to modify a pre-existing solver in this case. Okay, so there is also one tutorial, not one tutorial, but rather one case study on a solver modification. They have implemented a turbulence model within simple form and the scalar transport form. Okay, so they have merged two different solvers within one. Okay, so that is one thing. I'll show you which one it is exactly. So instead of going to lab migration in this case, you can go to case study, and under completed case studies, you can go down to case study number 130. Yeah, so you can go down to this one. Okay, you can go down to case study 130. This is done by Binayak Lohani. So he's also a student just like all of you. He had created a solver by merging simple form, scalar transport form, and he had also introduced a turbulence model within this particular solver. Okay. Now, as I said that in some cases, now scalar transport form is pretty simple when it comes to the FVM schemes and all of those things. But say if you want to incorporate something with simple form, you want to add temperature maybe in simple form, open form 9 solvers incompressible and simple form. Okay, so if you see in simple form over here, you can ignore the porous and SRF2. So these are two different solvers based on simple form. So that's why they are over here. But ideally, if you were to model or to modify your simple form solver, you would also have pressure equation and you'll have velocity equations. Okay, so these two files are also equally important when you're modeling anything with simple form or any of the flow solvers. So if you open simple form solver, the .c file, you scroll down. So over here you see that it is not exactly solving or not showing any equations over here. Whereas in your scalar transport form, you had the equations within this block and all. So over here, what we are doing is it's just including everything from the velocity header file and the pressure header file. So if you open see the velocity header files, so within the velocity header file, it is solving the equations. Okay. So to avoid cramping up this entire C folder, the C file, they have just created header files for each of these equations and they've written all the equations for each of those within themselves. Okay, and then they're just calling those equation header files within the .c file. So you can do that as well. So if you have too many equations, say you're modifying simple form with heat transfer and maybe even scalar transport form, having so many equations within your .c file will become a bit complicated, and if you have any errors then you have to skim through all of this code. But if you are doing this particular approach where you can just include the equation, so say you have flow equation, so you just have velocity and pressure. If you have any heat transfer equation, so you will add just energy equation header file, and within each of those files you will mention all of the FE schemes, or not FE schemes, but rather the equations for each of those particular terms. You can create that as well, and you can then call those header files within the C file itself. Okay, so over here they have still used FVM. Yeah, over here they've used FVC. So your finite volume calculus. Okay. So again, based on the type and what you're solving, the whether you're solving for implicit, whether you're solving it implicitly or explicitly, you can determine that on your equations or the type or term what you're solving for. So again, most of these are, or the discretization schemes, all of these are taught within a CFD course. If you have that background, it's always good for modifying any of these because you'll understand it much better. Otherwise, you'll always have to go through this document, read everything. In this document, it also explains what are all of these things. As you can see over here on top, it was explaining what is a Laplacian term or what is your divergence term and all of those things. So if you're interested in developing something from scratch in OpenFOAM, you can always see the programmer's guide. And if you're interested in running this particular case or any of the variants of this particular experiment, you can check the lab migration out. Okay. So again, I've linked, yeah, I've also added the steps for the solver modification part. So if you have the video, you can obviously look at the video. But in case you are not able to understand from the video and you require some steps, you can go through these steps. So again, you can create your entire thing, wclean, wmake to execute your solver. You can also search solver by their name. So within a solver, if you want to find a particular equation file, so in this case, you saw for velocity, for simple form, you had the velocity equation. So say if you want to find something similar to that, you can use the command grep, grep -r, and then you can just type in the equation or the file name that you want to search for, and then just type and it will search it for you within that folder. Okay. And over here, there are some links for the programmer's guide. Also for the lab migration that I just demonstrated, there are multiple experiments. So this one was just using a simple single scalar. There is an experiment in which they have used two different scalars as well. So you have half of the pipe with scalar 1 and the other half of the pipe with scalar 2. So that experiment is also there. You can check that out if you're interested in learning scalars or chemical reaction as a whole. And then you also have the OpenFOAM ESI documentation and foundation documentation. So these are all beneficial when you're modifying something, because some dependency files are always required for modifying any of these solvers. So you can find those in their documentation. Okay. So this was it about solver modification. So thank you, everyone. So this was it about solver modification and OpenFOAM. So you've learned from basic all the way up to an intermediate level in OpenFOAM, how to execute files, how to run files, how to copy them, how to modify them. So if you're following all of the videos and all of the files and setup that we've shared till now, you should be able to at least run a simple simulation up to a complex level, yes. And up to a certain level, you should be able to also execute and create your, or not create, but rather modify a solver itself. Okay. So I hope that this session is helpful for all of you, and that you guys try and learn OpenFOAM as well. So thank you, everyone.